All right, everyone. I am here with Georgia Gkioxari. Georgia is a research scientist with Facebook AI Research, aka FAIR. Georgia, welcome to the TWiML AI podcast.
Thank you. Thank you for having me.
I'm really looking forward to our chat. In particular, this interview is a direct result of a listener request. Listener wrote in to us, suggested that we get in touch with you to learn more about PyTorch 3D and what you're up to there. But before we dive into that topic, I'd love for you to share a little bit about your background and how you came to work in computer vision.
Sure, absolutely. I think it all started maybe 15 years ago. I was a college student in Greece, in Athens, in electrical engineering and computer science. And I took this class on computer vision, which was an undergrad class, but it was covering a lot of breadth and a lot of topics in computer vision. And that's how I got really excited about it. And after I finished up, I said, I think I should apply for grad school. I really didn't know what that meant at the time, but I said, let's do it. And so I took a map. I was like, where do I want to go? And I want to go to California. So I applied to schools in California for a PhD. And a few months later, Jitendra Malik emailed me saying that I was accepted and that he'd love to have a chat with me or talk about, if I have any questions. That email went to my junk because I never had received any email from that address. But I found it. I don't know how, but I was probably obsessing with my email inbox and junk, trying to get all of the response from the schools. So a couple months after that, I was on a plane, started my PhD with Jitendra Malik on computer vision topics that I started before the deep learning era, when we were still doing very complicated stuff, and it was actually much harder to publish at the time. And I finished my PhD in 2016, and then joined FAIR, first as a postdoc, and then now as a full-time research scientist.
Awesome. Did you realize at the time when you got that email that this thing that you were going to go study, machine learning, may have gotten in the way of you going to study machine learning?
Right. Not really.
What an awesome story.
Yeah.
Tell us about your work at FAIR. What kinds of things do you focus on?
So actually, even before FAIR, when I was doing my PhD, I really enjoyed recognition. This means object recognition, scene recognition. And what that means in general is trying to teach computer systems how to translate images or videos into semantic concepts. So, an image is nothing else than just a collection of random values. So there's a lot of work in order to go from that into understanding objects or scenes or properties, and any other semantic knowledge that we wish to extract from that input. So I've been working on that for now almost 10 years, first with different approaches than deep learning. Then deep learning came, and now we're using neural networks to do a lot of this stuff. And at FAIR, I'm sort of continuing in the same direction, really interested in enhancing recognition and building systems that can understand better and better.
Awesome. Now we've talked about this story of kind of pre-2012 computer vision, post-2012 computer vision quite a bit on the show, but is there anything that strikes out for you in particular in your work and experience of, this transition to deep learning?
Oh my God, everything changed. Everything. It was, so, before 2012, the predominant way of doing object recognition was with models that we call DPMs, deformable part models, I think. Mm-hmm. Yes. Oh my God, I forgot already. And it was really a struggle to sort of build on top of that. It was not as easy to enhance them, to improve them. It was a very difficult pipeline altogether to get anything really impressive or even a delta actually in performance. And then after 2012, it was so, everything changed. Things become a lot more modular and a lot more, you really didn't have to build a big pipeline. It was all sort of end to end, nicely working together. And of course, we also we were fortunate enough to have really nice open source tools and libraries that allowed us to, you work on a project, you release it, and now I can take it and really easily build on top of that. So that led to just an amazing progress in the field.
Even before there were things like OpenCV, did those play in the kind of work you were doing?
They did, and they were open source libraries for sure, but they were extremely complex. And in order for you to make any change, you had to understand it very well, which made it really difficult to develop new ideas. That was my experience. Maybe some of the audience will disagree, but I remember reading very complex papers on graph inference and all these things that really didn't end up doing a lot of, they didn't contribute to a lot of improvements, but we were trying our best.
Yeah. Awesome. And so tell us a little bit about PyTorch 3D. Why?
Yeah, well, of course. Oh yeah, that's what I'm here for. So as I said, I work on recognition, which means trying to understand objects, people, actions, so nouns and verbs, everything from an image. And if you really look into what recognition has done in the past few years, is it has really, and it's tremendous, the progress that we've seen, but our models make predictions on a 2D plane. So they treat as if the whole world is projected on 2D, and now we can mark with a 2D bounding box, oh, there's a person here, there's a dog here, or this person is running, but it's all in the 2D plane. And also this really nicely fits with convolutional neural networks and grid-based libraries that like PyTorch and TensorFlow, and most of the operations like convolutions are assuming that there is a grid. But if you want to move away from that, if you want to actually make predictions in the 3D space, so you no longer want to understand an object by its bounding box, but you might want to understand an object by predicting its 3D shape. Now, all of a sudden, you need to do very different things than what you were doing with a CNN. For example, 3D data is actually, they are graphs. So you have your points that those points live in 3D space. You have edges that connect these points. And now if you want to do any sort of computation on top of them, now you need very different tools. And you want these tools to be efficient. The same way PyTorch is efficient, you want 3D operators to be efficient. So we started looking into how we can recognize objects in 3D. We started having papers like Mesh or CNN, which try to move in this direction. And we found really quickly that we didn't have a lot of tools and a lot of efficient libraries for this. And this is how PyTorch 3D came to life. We decided that we need to enhance PyTorch and other deep learning libraries with the ability to perform efficient computations on 3D data. And that's not just it. Then you also want to be able to go back from 3D to 2D in a differentiable way. So now this is graphics people have been working a lot on rendering. But now that we have gradients and we need to optimize, you need these rendering pipelines and rendering operations to be able to have gradients, which means that you need to rethink a little bit about how you have defined these traditional graphics functions. You might want to change them, and you also need to make them very efficient. And all that is sort of what PyTorch 3D is all about.
Awesome. I've had several conversations on the podcast around trying to apply deep learning and machine learning broadly in kind of non-Euclidean 3D domains, like there's the gauge equivariant stuff, and there's another. I'm trying to remember the model where it kind of thinks of everything as a cardioid, kind of something shaped roughly, heart-like, and there's a Python toolkit around that. I'm wondering, does PyTorch 3D borrow from any of those kinds of ideas, or is it a kind of going in a different direction?
Yeah, so PyTorch 3D basically can actually take as data any data that is beyond the 2D grid. So, for example, a lot of people are working with volumes from medical imaging or from any sort of other sources of input signals, and this is where sort of PyTorch 3D is coming into play. And we actually have a lot of issues on GitHub where people are trying to get a variety of data that we've never thought about before. So I think that it has allowed people to actually do a lot more things. I think we also have to do a lot of work to keep building it and keep supporting even more signal and inputs. But I think it definitely ties to a lot of these problems.
Are the data sets that folks are using, do people tend to come at it with kind of these native 3D data sets, or are they data sets that, and I mean, might mean something like, something coming out of, a 3D sensor of some sort, or, a point cloud or something like that? Or are there use cases where folks, are starting with 2D and kind of annotating into 3D space? I'm not sure if that even makes sense.
No, it does make a lot of sense. And it's actually both. So,
okay.
So I think one thing that we wanted to focus on with our library is that one is the ability to be able to use these the data that comes from sensors, like what you said, point clouds or scans of, there is companies like Matterport that scan your house if you wish to. So this is the type of data that we are supporting in PyTorch 3D. And this is sort of more the straightforward use of trying to process the data with our library. But another use case is if you want to inject 3D data in the middle of your network. So if you want to reason in a latent 3D space instead of an explicit 3D space, that is also a possibility with this, with our library. And it's a possibility because all of our operators, are differentiable. So you can actually put them in the start, in the middle, at the end, anywhere you wish, and you can build your network. So the things that you can do are sort of endless.
So what's an example of what you were just describing, where you might want to have the latent 3D space as opposed to the explicit 3D space in the middle of your network?
Mm-hmm. There is a lot of applications that require this, and we actually had a paper in this recent CVPR 2020, which was joint work with our intern at the time, Olivia Wiles, and Rick Zaleski and Justin Johnson, where the problem that we wanted to tackle is novel view synthesis. So I give you an input image, and you want to hallucinate or think, or actually the computer wants to hallucinate what the scene will look like if you turn around or if you move straight up. So, which means that you have to generate new images that are geometrically and semantically consistent with your initial view. So walls need to be, vertical, the lines need to be straight. So objects might get unoccluded, so you actually need to complete them. So it's a very difficult task. And there we found that actually trying to do this just in an image-to-image approach, like pix-to-pix, and just putting a GAN there to help the system hallucinate was not enough. Actually, to capture that geometry and to make the network geometry aware, we had to inject this 3D latent space, like in reasoning in that space, in order to make that happen. And this is exactly what we did. So we try to reason about a 3D point cloud that corresponds to the scene, and then manipulate that, so transform it, rotate it, in order to make it consistent, to make the node view consistent with the transformation that we wish to apply. And then we used rendering and got to that output.
Got it. I did a interview with Josh Tobin at NeurIPS last year on geometry aware neural rendering. Sounds like the same setup or problem.
Yeah. I think that it's a space that is growing. There is a lot of excitement in the field about the potential. There is some recent work also. I don't know if you've seen NERF. They're able to sort of generate beautiful continuous scenes from just 2D images. And again, you need to use a 3D to reason in 3D and render back differentiably. So I think it's one of the exciting fields to be working on right now in computer vision and AI.
Mm-hmm. Are there...
Okay, but I'm biased, so it's just my opinion.
Are we at the point where we're starting to see commercial use cases of this, or consumer-facing use cases of this kind of thing, or is Facebook using it? Like, how mature is it, or how far are we from, seeing those kinds of uses?
I want to say yes, but it will be wrong.
Yes,
I think
yes.
I think that there is demand.
Got it.
Definitely, they want to be using it. Are we there yet? I would say not yet. Okay. Because when you talk about a product and making this work, you need to make sure that it actually works. So this is one part of my experience as being a research scientist at Facebook. Even though I don't work on products, I've realized that putting technology into products means that it really has to work.
It's a whole different ballgame.
Exactly. But I'm very confident that there's demand, so there will be progress, and I think we're going to get there.
Is the audience then for PyTorch 3D, is it primarily used by researchers, or is it used by developers, people who are building things?
I think currently it's actually being used by both. There is definitely some aspects of usage of PyTorch 3D that can make it and that are probably making into products. But I don't think that, have we solved AR, VR? Or can we build AR, VR experiences that are, the best ever? I think this is sort of, for me, this is the goal or the bar. And I think this is where we're not there yet. But I think there is definitely space for smaller impact in product for usage, but definitely also for researchers and developers.
Mm-hmm. Can you maybe take a step back and talk about how this fits in more broadly with kind of the drive to give computers, better means of perception?
Yeah, definitely. So I think we since deep learning sort of exploded, we've seen a lot of works and a lot of progress in making recognition work in 2D. Like ImageNet classification, we had AlexNet, VGG, ResNets, all this has been on a steady increasing path in terms of performance. And the same thing with recognition of objects, Mascar CNN, and then all the other following works that have made recognizing objects in 2D awesome. But in order to make these systems work, what we are doing currently is that we're annotating images. So we're asking annotators to mark what is the object and what of the object type, what's its mask, and then we're forcing networks to imitate this and imitate sort of the annotators basically. Mm-hmm. So 3D might be a way out of this. So if we can manage. Because if we can manage to reason in 3D, then we can actually understand objects more naturally. So I try not to bring a lot of parallelism to how humans learn, because I don't think that what we do currently is very similar to that. But
Mm-hmm.
how did you learn what an object is? So you were grabbing objects a lot, and you were rotating them, and you were looking at them from different viewpoints, and that allowed you to have an understanding of consistency and boundaries, and also semantics at the same time. So if I show you an object that you've never seen before, you will probably still recognize what it is or what the mask is, even though you might not be able to classify it. This is something that we can do today, but maybe through 3D, which is a more natural space to reason, we can expand our recognition ability. I don't know if that makes sense. It's a big bet, but it's sort of the hope.
I'm hearing that as, we've made a lot of progress in 2D, but 2D is kind of fundamentally you've tossed away a lot of information, and it's not just a lot of information in terms of bits. It's a lot of information in terms of the semantics of the objects themselves, and you're theorizing that by using that information or building systems that can take advantage of that information, those systems will be, I think what you're saying is not just maybe more accurate, but more closer to what we might think of as intelligent. Like they're making, they're solving tasks based on something more fundamental.
Exactly. I think, yeah, you said it very well. I don't have, it's a hope, and we don't have proof yet.
Right,
That's the
right.
case. But, even if we are able to learn with fewer labeled examples by reasoning the space, that will be a huge win.
Mm-hmm. Is that the primary win that would, if you demonstrated that was true, would the primary win be greater sample efficiency, or would there be other, how else might you expect that to express itself?
Yeah, definitely. So trying to learn with fewer labeled, fewer annotations, try to learn and generalize better. Generalization is something that we currently can't do very well. So there is a lot of axes that you can show this. Hopefully we'll show that in all. We'll see.
Yeah. Can you maybe walk us through the user experience of PyTorch 3D, and maybe starting from the, when you look at the way folks have been using it, what problems are they typically trying to solve? And is it kind of a drop-in replacement for PyTorch, in 2D? Are they doing the same things, or do they need to think differently fundamentally about the way they're doing stuff?
No, that's a great question. It's complementary. So it's an addition to PyTorch. And so it in terms of the user experience, so first of all, I want to say that this is work led by our awesome engineer, Nikila, and she has put up a lot of videos online on tutorials, how to get started. I just wanted to put it out there for people that are interested in using it. In terms of philosophy and how to use it in a broader sense, it's complementary to PyTorch. So our operators, we wanted them to have the same modularity that PyTorch has, where it's like little operations that you stack one after the other. It blends very well with PyTorch, so you can have a union of PyTorch operators and PyTorch 3D operators in order to do what you want. And then you can put this all together. You can implement a training loop, and you can train this all end to end. So it blends very well. And this is actually what we do. This is what we do in all of our papers that use it. It's a combination of many PyTorch and many libraries that build on PyTorch and PyTorch 3D.
Okay.
And yeah.
Go ahead.
No, that's
no, you.
No, just wanted to say that in terms of how people have been using it. We launched this in January, and so the best way for us to know how people use it in the community is through our engaging with them through GitHub. And we see that they're using it in all sorts of ways. They're using it for robotics. They're using it for graphics applications. Some are using it for medical. I know there was issues about some people wanted to reconstruct teeth and wanted to actually understand better how they can capture information there. So it's like the range is wild.
Do you have a favorite paper that uses it?
Yeah, well, I think that one of my favorite papers is our recent CVPR 2020 paper with Olivia. I thought it was a very nice way of blending in all the stuff that people have been doing in the GAN world of trying to create beautiful images, but making it harder by explicitly demanding geometry-aware outputs.
Got it. And so this is, it's a tool that's used by folks that are building stuff as well as doing research. But were there research challenges in building the tool, or is the tool kind of an implementation of stuff that you already knew how to do?
No, it was, and this is why it is a library on its own, is because in order to make a lot of this stuff efficient, in order to make a lot of this stuff work and train and backprop in a reasonable time and using a reasonable memory, we had to hack in there and implement custom CUDA kernels. And so it wasn't just building on top of PyTorch or on top of what PyTorch provides. We really had to do customized implementations to support all of this.
And so the CUDA stuff is that's low level, very low level work to get all this to work.
Oh yeah, definitely. I don't think you can. I think assembly is a step below that. Yeah.
And is there it's a good example of this, like a 3D equivalent of Dropout or something that you had to figure out to make this kind of stuff work, or is it all of your 2D things, generally apply? You just have to do this low level stuff to make them work in reasonable time.
So both of them were example cases. So in some it was things that you could already know how to do with other implementations, like with using PyTorch, for example. But then it would take just an incredible amount of time. So for example, in our Measure CNN paper, I'll calculate it that without PyTorch 3D, a network that I trained in 3 hours would probably take me 2 weeks. So this is sort of the scale that we're talking about. And when you talk about 2 weeks, you can't do research like that.
Yeah.
You can, that's just impossible.
And so in that example, are we talking about what was the before case? Was it a problem that's natively 3D that was kind of forced into 2D and done inefficiently, and now you're able to do it natively 3D? Was it you treated it natively 3D before, but using inefficient stuff in the Python domain, and you speed it up by going down to CUDA? What gives you the advantage in this particular case you're thinking of?
So I think that was sort of, again, both. But yeah, so it was just the fact that a lot of the existing implementations were not meant to be for the type of data that we had. So they immediately become inefficient. So for graphs, for example, it's not a very it's not easy to apply existing operators. And it was also the fact that the scale that we were talking about. So our graphs are very big. So you really need to make sure that you have very optimized implementations for that. And then I also wanted to mention that there was, for our differentiable render, which is also in 3D, in PyTorch 3D, there it was not a matter of sort of that stuff that you couldn't do with naively. So you had to actually write your own custom stuff in order to make the rendering pipeline differentiable.
Got it.
Yeah.
We talked a bit about graph here as being fundamental to working in 3D. Are there broader graphical uses and implications of PyTorch 3D that aren't necessarily, 3D in the way we think of it, visual data?
Yeah. So basically, you can think of a graph not necessarily as it being 3D. You can attach any vector to your vertices. So it can be a graph in this high dimensional space. So all that falls under the definition of a graph. And so this is sort of, so when I mention graphs, I mean that you have the ability to operate on data structures like that.
And are many of the folks that are using it in this, again, non-fundamentally, visual 3D sense, using it as just a generic graph tool?
Yeah, and I think this is, again, the exciting part. And when we talk about implicit representations and latent reasoning, this is what we mean, where you have a point cloud or a graph that doesn't have values that can be interpreted by like the human brain, like RGB colors, for example, but it can be any sort of feature vector. And so now this is where the interesting applications come in and the interesting stuff that people do.
Awesome. You are also, kind of going back to your background and your work more broadly, you are also a program co-chair for CVPR 2021 next year. And we were talking a little bit about this before we started recording. This is actually something that you've been doing since well before this year's CVPR. Share a little bit about that process. What does it mean to be a program co-chair at a conference like this in terms of, what you're thinking of and how is it?
Yeah, so correct. I was invited to be a program co-chair for CVPR 2021, which is next June.
Yep.
And as you said very correctly, work here starts 2 years before the conference actually happens. And I've been told that the work ends the year after. Again, I'm just like stressing myself out here. So what it means to be a program co-chair. So we are the program chairs are responsible for putting the program of the conference together.
Mm-hmm.
That means that we are in charge of the papers that will be presented. And what that means is that we are in charge of everything that needs to happen so that authors can submit their papers. And these papers need to be reviewed and a decision needs to be made. So what that means is that we need to make sure that we have the right infrastructure to do this. We need to make sure that we have the right and big enough reviewer pool of good reviewers that can offer reviews. And we also need to have a pool of area chairs. These are sort of the people that take a batch of papers and they are in charge of making sure reviewers do their job and that a decision is made after discussion and after discussing with other area chairs and with reviewers as well.
And are you doing anything new in terms of the reviewing process? I mean, this is something that's evolving in academic communities, open reviews and things like that. And whenever, review season comes around for Conference X, you see a lot of conversation on Twitter about the process.
Right.
What's your take on all that?
Right. So I think this is where the challenges come in. So a lot of the conferences in the past have built up rules that because they were trying to target a relatively smaller audience, not only the audience for the conference, but also the number of submissions. Mm-hmm. And now that we have the scale that we have, which is we've gone from like a couple hundred submissions like 10 years ago to 10,000 submissions this year. That's what we're sort of expecting. It's not just about scaling. It's not just about scaling all of this to make the numbers, make sense. That doesn't work. So we need to rethink a lot about our procedures and what we do. And we need to make sure that while we harvest all the positive from a growing community, that we're also cognizant of the negatives. And there's a lot of negatives. So we need to be able to foresee and have rules in place in order to deal with those issues.
Yeah, this is something that we've seen larger conferences like NeurIPS, for example, have to grapple with over the past couple of years, including, changing the name of the conference.
Correct. I think this is, for me, the biggest challenge is how to make it into, other than making this, the process be a success, is how can we ensure that everybody feels good being here. And like one of the senior computer vision scientists says, all you need is one person misbehaving that can ruin the experience for everyone. And when you have 7,000 people in a conference, the chances of that happening are much, much bigger. So this is a big challenge.
And are you planning for it to be an in-person conference?
I think that at this point, we're aware that in the best case, it might be hybrid, but probably it's going to be a virtual conference.
In June 21.
Yeah.
Wow.
Yeah.
Awesome.
Yep.
Cool. Well, it's been wonderful speaking with you. Any other parting thoughts on PyTorch or CVPR or any of the other things you've been working on?
Not really. I think, as I said, it's an exciting field we're in this exciting direction, the direction of 3D to be working on right now. So I'm hoping that, the bet that we just talked about, like, can 3D help us recognize better? Like, I hope to see more results in this direction. And, if somebody is thinking out there, oh, what should I work on? Like, what are the good problems to work on? I think this is a good problem to work on. And in terms of community and us, existing together peacefully, I hope that we all can figure this out. It's going to be a collective effort. So, yeah.
In terms of that previous point you made in prior problems to work on, are there more granular or specific directions that you might suggest someone who, hey, I like computer graphics and 3D and machine learning? What specifically needs to be addressed that you think are kind of ripe opportunities for folks to jump into?
Yeah, I think that what is, in my view, one of the unsolved problems right now is doing this at a large scale and from in the wild data. So, take the millions of images that we have in our databases, and how can you make 3D, either predicting in 3D or reasoning in 3D space, contribute there in whatever downstream task that you wish. So I think this is one of the biggest challenges, making this work in the wild and making this work large scale, the same way that we've seen 2D problems benefit from this large scale training.
Awesome. Well, Georgia, thanks so much for chatting with us about what you're up to.
No, thank you for having me and for listening to me.
Thank you.